Nithin.
Yeah, thank you for the introduction. It's good to be back in Sydney, and thank you for accepting me to speak today. Today I'll talk about constant overhead fault-tolerant quantum computation with reconfigurable item arrays. This is joint work with all these amazing people, and you can find the paper on the archive under that link. So to get started, what's the challenge of large-scale quantum computation? The current physical error rates of the qubits are around 10 to the power of -3. And to run any of the large-scale quantum algorithms that are interesting, we need to get to like between 10 to the power of -12 and 10 to the power of -15. And engineering better physical qubits alone will never get us there. So we turn to quantum error correction to bridge the gap. And in our work, we aim to bridge this gap using non-local key LDPC codes. And in particular, we propose an implementation blueprint for memory and logical gates on a neutral atom quantum computer. And the key idea behind the proposal is to use a dense QLDPC memory block to encode the logical qubits, and then extract, whenever we want to do a computation on a logical qubit, we extract to a topological code, like a surface code or a color code, through some mediating ancilla block. And in our work, we show that with this scheme, we can achieve order of magnitude better space overhead compared to a surface code scheme. So for example, what I'm showing on the plot here is I'm plotting the number of logical qubits of the algorithm we want to run on the y-axis, and the target logical failure rate of the logical qubit on the x-axis. And this is all for a fixed physical qubit error rate of 10 to the power of -3. And you can see that already at a logical failure rate of like 10 to the power of -5, with the QLDPC-based scheme, we require an overhead of like 2,500 physical qubits compared to like around 50,000 with a surface code-based scheme. So to understand these results a bit better, let's understand why we need to go beyond the surface code. So remember that an NKD quantum code uses n physical qubits to store k logical qubits, each protected to a distance d. We define the rate of the code as k over n, and we can make it an asymptotic quantity by taking n to go to infinity. Good codes are those where we have a constant encoding rate, so k scales linearly with n, and d also scales linearly with n. The surface code has a 0 asymptotic rate because we can only encode like 1 or 2 logical qubits, no matter the size. And like Litinsky points out in his paper, because of this low encoding rate, any scheme to run like large-scale quantum algorithms with surface codes requires like millions of physical qubits. And it turns out that for 2D local codes, there is the BTP bound, which is saturated by the surface code. So if we want to look for codes that are better than the surface code, we need to look outside of 2D locality, while of course preserving the low density parity check nature of the code. In our paper, we studied two main non-local QLDPC codes, hypergraph product codes and lifted product codes. In this presentation, I'll focus on hypergraph product. So the hypergraph product code is a quantum code constructed from 2 input classical codes. And here I'm showing the construction. Suppose we have 2 classical codes. The open squares are classical checks, and the open circles are classical bits. And we draw a connection between the check and the bit, if that bit is in the support of the check. And we construct the quantum code by making a grid. And at the intersection of a check and a check, we put a qubit. And at the intersection of a bit and a bit, we also put a qubit. And of a check and a bit, we put a Z stabilizer, and of a bit and a check, we put an X stabilizer. And then the connections, so which stabilizers check which qubits, are inherited from the base classical codes. And they look the same along rows, and they also look the same along columns. So if we take 2 classical repetition codes, we recover back the surface code. But if instead we take 2 classical codes where the number of encoded logical bits scale linearly with n, we can get a quantum code with constant rate. And we construct these codes in our work. In particular, we look at classical codes from random 3-4 tanagraphs, which simply means that the degree of each bit in the tanagraph is 3, and the degree of each check is 4. Okay, so now we have these non-local codes. We need an architecture to implement this. And a very promising and rising architecture is this neutral atom array platform, where the qubit levels are defined on the hyperfine levels of neutral atoms. And they're trapped in optical tweezers, which can be moved around easily. They have order second coherent times. Single qubit gates can be locally addressed using Raman pulses and have fidelities like above 99.9%. And two qubit gates are performed by bringing the two atoms we want to perform the entangling gate on together and then shining a global pulse. And if the atoms are together, they get excited to a Rydberg state and the entangling gate is performed. Otherwise, an identity gate is performed on the qubit. And recently it was demonstrated that we can achieve a fidelity of like 99.5%. So Dolev tomorrow will speak about some recent exciting experiments that were performed on this platform and are yet unpublished. But I'm showing an example, and also Harry has a poster on Tuesday. I'm showing an example here of GHG state creation with logical qubits. So the circuit goes as follows. We have 10 input steam codes, so 70 physical qubits. And then we prepare each steam code non-fault tolerantly using a similar circuit to what people have said today already. And it includes 3 layers of entangling gates. Then we perform, to make it fault tolerant, we perform steam-like error correction, where we have some ancilla blocks here used to detect the errors. And we do this by using transversal C0 gates, which is what is shown here. And then we move the ancilla qubits to storage away from decoherence. And on the top 4 qubits, 4 logical qubits, we do the GHG state circuit, which involves the transversal Hadamard and also transversal C0 gates. And you can see on the movie here, 1, 2, and 3 layers of non-fault tolerant encoding, followed by the transversal C0 gates for steam-like error correction, and then we move the ancilla to storage, and then we do the GHG state preparation. And in particular, what is interesting here is that moving the atoms is, we can move them around, and that's okay. But the enabling feature is that we have efficient classical control of multiple blocks in parallel. And this is very important, for example, in our work with hypergraph patacodes, because we know that the hypergraph patacodes are not completely random. There is some structure in them. And in particular, things lie on a grid. And checks connect either vertically or horizontally. And all column connections look the same, and all row connections look the same. So we want to make sure that we do things in as parallel fashion as we possibly can. So what we propose is that to, for example, implement the horizontal connections, we do column permutations to bring the qubit next to the check that we need to perform the entangling gate on, and then shine the global laser, and then continue rearranging the columns to implement all of the horizontal connections, and then move on to the vertical connections by permuting rows. So the only thing that is left to check is that we can permute these columns and rows in an efficient way. And we came up with a very quick algorithm where to arrange efficiently in a 1D line. So suppose that we have L qubits in a line, like shown here, and then some empty workspace. We can, the algorithm at each step goes as follows. We move to the right half all the qubits that in the final configuration end up in the right half. And then we compactify, and then we repeat the algorithm on each 2 sub-half. And because we're having the number of qubits at each point, this is a log depth rearrangement algorithm. So we estimated the time of 1 cycle of error correction with the hypergraph patacode using this method, and it's orders of magnitude less than the coherence time of the neutral atom qubits. And what I'm showing here is exactly like the procedure that I just described in the previous slide. So we're moving the atoms into the right location by permuting columns. And then once they're in the right location, we shine a global laser to perform the entangling ZZ gate. And then once we're done with the column permutations, we move on to the row permutations and then perform the full syndrome extraction circuit with the hypergraph patacode. What's cool about this movie is that the code used to generate the movie is compatible with like the experiment, so we can plug in the code directly into like the item array right now and run this experiment. Okay, so now we assess the circuit level. So now we want to assess the error correction capability of our scheme, and so we run memory simulations, where we aim to keep the logical qubit alive for a long time. And in particular, we encode some logical state and then do multiple rounds of error correction before reading it out transversely at the end. Within each round of error correction, we perform potentially multiple cycles of syndrome extraction circuit, followed by a decoding procedure and then application of the recovery operator. So in our simulations, we make use of of a key important fact of hypergraph product codes and other LDPC codes, which is this linear syndrome confinement property, which basically states that qubit errors cannot grow without triggering more measurement syndromes. And as a result of this, together with the fact that we're dealing with QLDPC codes, and so we have bounded check weight, we have both single-shot decoding and also single ancilla syndrome extraction circuits are fault tolerant, and we show this in our paper. And then to perform the simulation, we ran a BP and OSD decoder, where in the first rounds of error correction, we ran 3 cycles of syndrome extraction circuit, followed by a BP decoder. And then on the final cycle, where we assume noiseless measurements, we ran a BP and OSD decoder after only 1 cycle. And so to run these simulations on multiple cycles, and using BP and OSD, we leverage this like recent paradigm of space-time decoding to run the decoder on like the circuit level detector error model. So you can see the result here. We're plotting on the y-axis the logical failure rate of the entire QLDPC block. So if any one of the logical qubits of the block fail, then we call that a failure, and against the physical error rate. And we obtain a threshold of around 0.6% under circuit level depolarizing noise, where we assume no idling errors. If we do include idling errors, and in particular realistic idling errors, where they scale with the code size, then it produces minimal changes, mainly due to like the long coherence time of the atoms. And what I'm showing on the plot here, so the way that we can model this realistic idling noise is by rescaling the physical error rate here. And you can see that things don't lie on a vertical line, they're slightly shifted. And the bigger the code size, the more we rescale the physical error rate. But you can see, for all practical purposes, that below like the threshold of like 0.6%, we can still obtain exponential suppression. And more importantly, if we look at the overheads, first without any extrapolation. So if we look at the overheads, we again recover back the plot that I showed at the beginning. And this plot is like the minimum overhead of the hypergraph product code, and also the lifted product codes that we run in the paper. So the point that I showed at the beginning is without any extrapolation, is for the lifted product code. And you can see other results here with no extrapolation. So on the top row, we're showing the target logical qubits of the computation. And then the next row is the target logical failure rate. This is all for a fixed physical failure rate of 10 to the power of -3. And then we show the overheads for the hypergraph product codes and the lifted product codes. And we also put a multiplier to show the factor saving that we have compared to the surface code. So, so you can see that QLDPC codes start outperforming the surface codes at several hundred physical qubits, as shown by like this example of the lifted product code here. We also have order of magnitude savings in a large region of this phase space. And we require less than 100,000 qubits are enough for 1,000 logical qubit computation. So for the huge number of physical qubits around the border of this phase space, we did extrapolate the results, and we extrapolated for the hypergraph product code. Okay, so memory is nice, but we also want to do computation on the logical qubits. And again, what we propose is that we have a dense LDPC memory, and we have topological codes as the processors. And it turns out that if we operate on a small enough number of these topological codes at the same time, we can still maintain the constant space overhead of the QLDPC memory block. Our contribution is a qubit-efficient teleportation scheme between QLDPC and surface code. And we also, by simulating this teleportation procedure, we demonstrate the first numerical simulations of doing computation with non-local QLDPC codes. So to understand this teleportation, we turn to measurement-based schemes. So it turns out that measurement-based gates are universal, and yeah, so all we need is single and joint Clifford measurements. So for example, like the circuit I'm showing there is the implementation of the CNO gate using only like XX and ZZ and single X measurements. And then the question is, how can we implement these Clifford measurements on logical qubits? And we turn to lattice surgery for that. So the trick with lattice surgery is that if you can identify a logical operator at the boundary of two codes, and the boundary looks kind of the same, you can like merge the codes, and then the logical operator becomes a stabilizer of the new merged code. And because we know how to measure stabilizers fault-tolerantly, we can measure the logical operator fault-tolerantly. And then we split the codes and continue on with the computation. So teleportation can also be done through measurement. But the problem that we run into is that the boundary of the QLDPC code can be very different from the boundary of the surface code. And then the question is, how do we merge these two? And this is the scheme that we came up with. So suppose you have the QLDPC block here, and let's identify logical X at the boundary. And then you have the surface code here, and identify logical Z at the boundary. We can associate a logical operator with a classical code by mapping the qubit in the support of the logical to classical bits, and the checks incident to those qubits to classical checks. So we can map logical X here to classical code C1, and logical Z2 here to classical code C2. And then we construct a new code by taking the hypergraph product of C1 and C2, and we call this the ancilla block. And by the nature of the hypergraph product, all the columns of the ancilla block look exactly like the logical of the QLDPC code, and all the rows of the ancilla block look exactly like the logical of the surface, so repetition code. And then we can perform direct lattice surgery between QLDPC and ancilla to implement a logical XX measurement, and between surface and ancilla to implement a logical ZZ measurement. And it turns out that that's all we need to do teleportation between these two codes. So here's a teleportation circuit where we are teleporting, for example, from the surface to the QLDPC code. And the only things that we need are, again, this XX lattice surgery measurement and ZZ lattice surgery measurement, together with some single Clifford measurements, and then some feed-forward corrections at the end. So we also proved that this lattice surgery procedure is fault-tolerant in the paper. Okay, so we ran this teleportation simulation by simulating noise on the lattice surgery between the QLDPC code and the ancilla block, so during this MXX measurement. And you can see the result here. We're again plotting logical failure rate of the entire QLDPC block on the y-axis, and physical failure rate on the x-axis, again rescaled to include the effect of idling errors. Okay, so I should also say that to run these simulations, because the QLDPC code is single shot, but the ancilla code is not single shot, and then when you merge the two, the result turned out to not be single shot. So we had to repeat measurements d times in order to be tolerant to measurement errors. And that's where this like space-time decoding procedure turned out to be very useful and actually key to decode this whole thing. And then, yeah, so we see that we can maintain the competitive thresholds and low error rates that we saw in the memory setting, also in this computational setting. So to summarize, so there's a lot of like rising hardware platforms and exploring these like LDPC challenges and opportunities on near-term hardware will become very important. And I have a few points here. So space-time trade-offs. So QLDPC, we can achieve constant space overhead, but that comes at the cost of poor time overhead. This could be okay in various settings. So if your algorithm is already, there's not a lot of gates being performed in parallel, then that's okay. Or if you value like space resources over time resources more, then that's also fine. Yes, looking forward to improving QLDPC computation through some of these schemes like directions, Russell gates, beta decoders, and preserving single shot when doing lattice surgery. So summary of what we went through today, and then thank you to all my collaborators. So Qian from University of Chicago also has a presentation in QC, and Harry and Dolev will speak more about the neutral atom platform later on. Okay, thank you for listening.
Hey, thanks for the talk. If you go back to like, I mean, don't worry about actually going back, but like when you're talking about the decoding, you mentioned that you do these like 3-cycle blocks, then you decode, then you do another 3-cycle block.
Yeah.
Is there a reason you don't just decode the full thing, or at least larger chunks, or is it more about scalability slash?
So here, so typically when you're doing like single shot decoding, like people just run one cycle per round. And then the reason you run multiple rounds is because you want to see like the sustainable error threshold, where initially, like if you run for a few rounds, the threshold might be higher than what it actually is. So you need to run for multiple rounds. But here we improved slightly on like the 1 cycle per round thing by doing 3 cycles per round, and we saw that like improved both the threshold and the sub-threshold scaling.
No, I'm saying why don't you do all of them in one block?
I mean, you can do all of them in one block, but you want to see like the sustainable error threshold. So you run multiple rounds. And also, okay, so also if you run, okay, let's say you run 1 round, and the maximum you would want to run of number of cycles is D, because if you run more than D, then that's like useless. So yeah, so you could envision like an experiment where you just run like 1 round, like D cycles.
Hi, thanks for the very nice talk. Can you go to the next slide? I think my question was on 11. Yeah, so I could just be reading this graph wrong, but naively I would expect the logical failure rate as a function of P to be like decaying 4 times faster, 4.5 times faster for a distance 18 code compared to a distance 4 code. But it doesn't seem like it is here.
So yeah, so I mean, we did check to make sure that like it fit the exponential ansatz. I'm not sure like reading it off directly from the plot.
I see. Okay, so
but yeah, and also like reading off directly from this result and doing like no extrapolation, we get the results that I showed on the next slide.
I see. Okay, so it is. Okay, so I read it off incorrectly. Sorry. Thank you.
Yeah, that teleportation idea was really cool. I was wondering, why could you not do all logic on your LDPC code using that idea? Why did you need to have like this processor that's made of surface code qubits?
So yeah, so we can do logic, for example. So even our scheme of like this like lattice surgery scheme, could in principle, like I showed before, gates are universal using a measurement-based approach. So we could use this lattice surgery scheme to not teleport, but instead like do the gate directly. In the paper, we pitched it that way because in like topological codes like the surface code and like the color code, we know how to do gates transversally, for example, very cheaply. And this is something that Dolev will speak tomorrow as well. We could in principle do it in the QLDPC, but again, there is restricted parallelism if you want to maintain the constant space overhead, whether you do teleportation or like direct lattice surgery approach.
How's the time to pull one of these qubits out into the your computation region? How does that compare to the amount of time it takes to do a, let's say, lattice surgery operation on a surface code?
The time
to pull one, so you have to pull out these qubits and then you do some operations on them and then you'll put them back in, right?
Yes.
So how does the time taking to pull the qubit out compare to the amount of time that you actually will compute on it instead? Like, is this going to be dominated by the time to pull it out, or is it going to be dominated by the time to do the operations?
Like if you do it transversely, it will be dominated by the time it takes to pull it out.
Okay.
And in particular, why it's that is because to be tolerant to measurement errors when you're pulling it out, you need to repeat the the measurement d times, and that's like the bulk of the time overhead is spent on that.
Okay, and so therefore you're nearly always going to be in the situation. Most of your time will be spent on pulling syndromes out of the code rather than just, let's say, keeping it as a memory.
Rather than keeping it as a memory?
As opposed to doing the error correction procedure for the topological code itself.
Yes.
Okay.
If you go to the plot slide again.
Where's the...
So, hello.
Oh.
Can you go to the slide with the plot again?
Which plot?
Back a couple, I think. With the performance. Yeah, this one. So the y-axis logical failure rate, is this word error rate or is this like per logical encoded qubit?
So we found that different papers use word error rate to mean two different things. So we just call it logical failure rate. But what it means is that if any one of your logical qubits of the block fail, then we call that a failure.
Okay.
And then we also normalize to the number of cycles.
Okay.
So
Thank you.
per cycle.
Yeah, thanks a lot for the presentation. So can you please go to the last slide? You mentioned that the time overhead is quite bad. So how bad it is?
The
Time overhead.
time overhead. So okay. So how many things can we do in parallel?
So I mean, like for so I understand, like if you want to scale up your code size, of course you need to move your atom for more times. So how does this the whole duration or the overall duration for one cycle of syndrome measurement takes compared with the coherence time?
Oh, I showed that in a slide. So the cool thing about like this atom array platform,
Yeah.
so like 24 milliseconds, which is less than the coherence time.
So
For
what
one.
is the code size here?
What is the what?
Code size. Code size.
Oh, this is for a 10,000 physical qubit.
Yeah.
So it's like 100 by 100. So like distance 100.
So I'm also wondering how does it scale up?
Oh, how does it scale?
Yeah.
Scales with the square root of the code distance.
Of the code distance.
Yes.
Yeah.
And this comes because when we move in the atom array platform, the movement is the time it takes to move a distance L is not linear in L, it's actually square root in L. Because the movement is not like a constant speed movement,
Yep.
it's like a constant acceleration movement. You can think about it that way.
Yeah. Yeah. All right. Thanks.
It's actually a kind of a follow-up question to the previous one, which is that I guess as you scale up the system, at some point, the time it takes to move your qubits around will exceed the coherence time. So at that point, you have to do some sort of extra step of error correction. Have you thought of what's the best way of doing that in your platform?
Yeah, so, okay. So in a paper, we have a figure addressing this. The point at which this occurs is for a physical, the number of physical qubits is like 1 billion. And at that point, you can already achieve a logical failure rate of like 10 to the power of negative 24. But if you did want to scale further, I think concatenation might be the way to go.